Just check the recording is paused. It has to be restarted. Great. Okay, great. Very good afternoon to all the participants once again. Uh, yeah, we will go ahead and continue from where we had left off in the yesterday's session. Okay. So in the yesterday's session, we were trying to derive. Okay, we were trying to derive the most important part of statistical physics, right? So that is partition function. So the partition function, the moment you know the partition function of any system, whether it is classical or quantum, okay, so whether you are dealing the quantum particles through Fermi-Dirac statistics or you are dealing with Bose-Einstein statistics, then the partition function would be very useful in calculating some average parameters. So let me revise for you just to have a connectivity. Okay, as we see, the system of particles exist in classical and quantum form. Okay, right? So the moment particles are classical in the sense they are large, they are described by Maxwell's Boltzmann statistics. Okay, and let's say if the particles are going to have a quantum form, inside the quantum form there are two ways. One is if they are going to have integer spin particles. Okay, those are like photons. So they were dictated by Bose-Einstein statistics. Okay, in case those quantum particles having half integral spins or integer spins, okay, right? In that case, they are dictated by Fermi-Dirac statistics. Okay, right? What we do, we will try to rederive once again what is a partition function for all these three cases. Okay, let me write down as we know the partition function, you can say the partition function for all these cases could be derived. Okay, and moreover partition function is a very powerful quantity, okay, which could be used to derive other parameters such as, okay, let me write down, such as what we had seen, average mean or mean particle number in a particle number. What it means is, or if I start arranging the particles in various states, okay, right? So let me understand that. If n particles are there, okay, and there are states with energy and there are states with energy, Okay, energies such as E0, or let's say I'll start with E1, not E0. Let's say there is a state with E1, there is a state with E2, there is a state with E3, and so on. I'm not going to talk about how long. Okay, and now out of n particles, okay, in state 1 there is n1 particles, in state 2 n2 particles, the energy of state, okay, a number of particles in a state. Okay, so these are the things one should n3 and so on. So likewise they may be distributed. Now as we know, partition function, okay, partition function would give us okay, the number of ways or number of possible ways the above could be arranged. Okay, right? So remember that, right? So now let me choose one way. What is that one way is, right? So let's say there are n1 particles in state 1, n2 particles in state 2. Now, as per the Max-Boltzmann statistics, now let's see in terms of Max-Boltzmann statistics the above scenario. What is that is, in the above scenario, let's say n1 particles are there in state 1. How many ways they can be arranged? Okay, n1 particles in state with, okay, with the energy E1 or epsilon 1. Okay, now as per the Max-Boltzmann statistics, all particles are distinguishable. These particles could be arranged in n1 factorial ways. Very simple. Okay, so as per Max-Boltzmann statistics, n1 particles, okay, arranged in n1 factorial ways. Remember that. Okay, so the moment I know that, the same story, similarly, let's say there are n2 particles in state with energy T2. So as per Max-Boltzmann statistics, n2 factorial ways, these particles could be arranged. Only I'm talking about in that particular state. Okay, right? So those things would apply for all other states. Now, as we know, the total number of particles are n factorial. Okay, so for n particles, there are n factorial ways could be arranged. Okay, so could be arranged. Now, these n particles could be divided among E1, E2, and so on. Okay, but if you don't bother about E1, E2 group or E3 group and so on, the way how many ways it can be arranged? N factorial ways. Now I am going to realize. Now I am going to bring in the condition within n particle. There are n1 factorial ways in one particular group. So therefore, overall ways arrangement, overall ways arrangement by keeping individual groups, okay, very important, individual groups of ER, okay, into consideration, okay. What happens if you arrange overall ways of arrangement by keeping individual groups of ER into consideration, I would be having n factorial divided by n1 factorial, okay, n2 factorial, n2 factorial, n3 factorial, so on. So this is the overall arrangement. When I'm considering within the overall arrangement, E1 is arranged n1 factorial ways, E2 states are arranged in factorial ways. So this is the just arrangement of the atoms, okay, for single arrangement. Now, the partition function would tell me this individual arrangement several combinations. Okay, so the partition function, now the partition function is, what is the partition function? Now the partition function in general is Z is summation over of all possible arrangements exponential minus beta inside the bracket E1 N1. Okay, so let me not put E1 N1 yet. I simply say ER, okay, ER, ENR. Okay, right? Okay, so yeah. Now I want to explicitly write down all the possible cases. So all the possible cases if you write down, which would be N1, N2, and so on. N1 factorial divided by N1 factorial, N2 factorial, and so on, multiplied by exponential minus beta. You see now E1 N1 plus E2 N2 and so on. So this is the overall grand partition function for Max-Boltzmann statistics. What I will do now, I'll just play a trick, algebraic trick, which is summation over all n1s and n2s and so on, n factorial exponential beta epsilon n1 divided by n1 factorial. Okay, so if you put this as a power, n1 as a power, we can do that. In the exponential case, power becomes exponent multiplicand. Okay, exponential minus beta e2 power of n2 divided by n2 factorial. Such terms are up there. Okay, all such terms. Now what happens? Okay, so n capital N doesn't depend on the exponential summation or anyway. You can send it out. Okay, what I left with is, right? What I left with is summation over n1 factorial exponential minus beta e1 to the power of n1 divided by n factorial. Such terms are there. Okay, let me write down. n2 n2 divided by n2 factorial overall. Okay, now if you see carefully, okay, this terms, if you see carefully, which appears to be like partition function, okay, right? Right, so this appears to be like partition function, okay, exponential minus beta e1 plus exponential minus beta e2 plus overall n. Okay, so we can simplify this into this form. So we are not going to the details how it is done. there is another way of deriving this also, because this one comes to this form if you start from here and then simplify. Okay, right? So now what is going to see is, now use this partition function, and if you derive what is the average particle number for Max Boltzmann, which comes out to be n into exponential minus beta epsilon s divided by summation over various possible r states exponential minus beta e r. So the numerator is where r takes the s value. I have written. This is the average particle number or mean particle number. Okay, mean particle number for Max Boltzmann statistics arrived using the partition function z. Okay, right? So, yeah. Now, what I want to derive for the same partition function, similar partition function. Okay, so if you understand the partition function for Bose-Einstein statistics, then you can apply that for Fermi-Dirac statistics. In that way, it becomes much easier. Okay, so what I will do, I'll just derive for partition function for first Bose-Einstein statistics, and then I'll show you how we can do it for Fermi-Dirac statistics. In that way, it becomes much easier. Okay, right? Now, what I want to do, what I want to do, I will just derive. Okay, 1 minute. Yeah. Mean photon number as per Bose-Einstein statistics. What I want to do, ns, average number we want to find. Now we will start with the very basic thing. Okay, what is that thing is, as per Bose-Einstein statistics, what is the thing? Particles are indistinguishable. Okay, and one more thing is, any number could be occupied in a given state. Any number of particles could be occupied in a given state. Okay, this is most important 2 points. Now what I'll have, I have, let's say, some particles. I will not say how many. Let's say, if you want, let's say we have n particles, capital number of particles. Okay, now those particles could be arranged in, those particles could be arranged in various ways. ns, ns could run from 0, 1, 2, 3, and so on. What is ns stands for? Ns taking 0 means there is a particle, there is a state with the E, E0. There is a particles with the state E1. There is a state with E2 energy. How many particles are there? 2 particles are there. There is a state with the E3. How many particles are there? 3 particles are there. Okay, right? So you can keep going this one. Now I want to find out what is the mean photon number. Even from mean photon number, you can get back what is the partition function would look like. But straight away you can write the partition function. It's not a big deal. Okay, partition function is usually summation over various possible arrangements. Okay, various possible arrangements. S taking various values, exponential minus beta es into ens. That's all. That's a partition number, partition function for you. Doesn't matter what are we talking. So this is in general partition function. Now I want to find mean photon number. So mean photon number is, let me write down mean photon number. Okay. There is a state with energy E naught. How many particles are there in that E naught state? Zero number of particles are there in that state. That means all the remaining. So, all right. So here ns stands for 0, where ns stands for 0, where the energy is 0. In that state, how many particles are there? 0 particles are there. All the remaining particles n must be occupied in the states except that particular state. So I'll write down a partition function Zs, okay, referring Zs is a arrangements possible with the exclusion of okay, es state. Okay, means the arrangement would be n1, n2, ns minus 1, ns plus 1, and so on. Okay, wherever there is a ns, the only that is state having a 0, where s stands for 0. Okay, in that state, no particles are there. All the particles are arranged in other states. So, what is the partition function for that particular situation? Zs. How many particles are arranged? N particles. Now, the next scenario. Now, there is a energy with a state. So, there is a state with energy E1. How many particles are there in that? Let's say only one particle is there. One particle. What is the arrangement? What is the arrangement of that particular case? That particular case is exponential minus beta E1 into 1. Okay. So the one particle is arranged in that, means there is no shuffling. So exponential minus beta E1 into 1 is the arrangement. What about the remaining n minus particle, n1 minus particle? They could be arranged in anything other than these states. Anything other than ns. So what is that? Zs n minus 1 particles are arranged in these states. Okay, similarly, there is a state with energy E2. Okay, 2 particles are there in that state. So what is the partition function for that 2 particle state? Minus beta E2 En2. En2 is 2 particles. Okay. Now, other than those 2 particles, remaining n minus 2 particles could be arranged in the given state, given possible arrangement. So that is Z S n minus 2. So this thing will go on divided by what? Divided by there is excluding. Okay. So see, what is the average number? Average number usually written as summation over ns exponential minus beta es ns divided by summation over, okay, summation over exponential minus beta es. This is the average number, right? Average mean number. So as for that, I am just trying to write down the numerator. I wrote down. The denominator is simply ignore 0, 1, 2, and so on. Just put remaining thing. Zs n plus exponential minus beta e1 zs n minus 1 plus exponential minus beta e2 zs n minus 2 and so on. So this is a average photon, as an average particle number as per photon statistics, as per Bose-Einstein statistics. Okay. Now let me do some algebra. What algebra I will be doing? Yes, I'll just take a common of Zs in the denominator and the numerator. Let me take in the numerator, this will be exponential minus beta E1, exponential minus, okay. So before doing it, let me write down that Zs n minus 1 divided by Zs n plus exponential minus beta 2 into e2 Zs n minus 2 divided by Zs n plus so on. In the denominator, Zs n 1 plus exponential minus beta e1 Zs n minus 1 Zs n plus exponential minus 2 into, sorry, no, there is no 2. 2 will not, because it is n will is there only in the numerator. B2 Zs n minus 2 Zs n plus so on. Now this 2 cancels. Now what I'll do, I'll introduce a factor. What is the factor? I'll just define Zs n minus 1 divided by Zs n as some exponential alpha s. What I mean is, this is some kind of a factor, exponential factor. It's kind of either decaying or, okay, it's either it's decaying, okay, it's like a decaying factor, right? So as you reduce the number of particles for the arrangement, okay, so rearrangements in the denominator would increase, in the numerator it decrease, so it's an exponential decay function, okay. So which implies which implies Zs n minus 2 Zs by n, okay. What is this? This would be equal to exponential, okay, minus 2 alpha s. Okay, by doing it, I will have ns is equal to 1 plus exponential minus beta e1 exponential minus alpha s plus 2 into exponential minus beta e2 exponential minus 2 alpha s. Okay, right? So the moment I reduce the particles, it gets multiplied. That's how I just define. Now plus so on. In the denominator, I will have 1 plus exponential minus beta e1 exponential minus alpha s exponential minus beta e2 exponential minus 2 alpha s and so on. Okay, right? So if you carefully write down the full form in a short, would be ns average is equal to summation over ns exponential minus beta e s, okay, beta e into ns, okay, and exponential alpha s ns, okay, right? So divided by summation over ns exponential minus beta es ns exponential minus alpha ns alpha s into ns, okay, right? Now we put the terms, exponential terms together, what you would be getting? Summation over ns into exponential, you can take ns common with the minus sign, beta es plus alpha s. Denominator also summation over ns exponential minus ns, if you just take common, beta es plus alpha s. Okay, so this is the average photon number as per Bose-Einstein statistics. Okay, now what is its final form? You can really find out its final form. You can get rid of the summations. We did it earlier, which is going to be equal to, you see, how did I find out? How do I find? If you carefully see this, in the denominator, one factor is extra factor is there, that is ns. Numerator and denominator both are same. Now what I'll do, if you just take summation over ns, exponential minus ns, beta es plus alpha s, if you just take, if you just differentiate this factor with the beta, okay, right? If you okay, not beta, if you differentiate with the yeah, okay, if I differentiate, I'll get ns, yeah, yeah, for sure, yes, okay. So yes, just a minute, let me check how we did last time. Yeah, differentiate with the es, differentiate with the es, okay, right? And then you differentiate and you multiply it by 1 by beta, you will get the numerator, okay? So this is equal to the numerator. So from there you can arrive what is the ns would look like. Ns would be simply, okay, let me write down the expression exactly. Bose-Einstein statistics, case of Bose-Einstein statistics, which would be, 1 minute, okay, I want to make sure that the expression is correct. I'm just looking at the what I have written, okay. 1 minute, yeah, comes out to be 1 divided by exponential minus beta es plus alpha s minus 1. This is a Bose-Einstein statistics. Now, for a Fermi-Dirac statistics, we'll derive. Okay, right? So we'll keep this aside. Let's go to Fermi-Dirac statistics. Fermi-Dirac statistics based mean photon number. Okay, that is what I want to find. This is BS. You remember that. Okay, now mean photon number. Again, let's take the number of particles is, okay, number of particles, let's say n particles are there, and among n particles, how are we going to arrange? That's a question you should ask ourselves. Okay, now first of all, let's find out what is the Fermi-Dirac FDS. FDS is particles are indistinguishable, indistinguishable, okay, and but the thing is they are indistinguishable, but no two particles in same state, okay. That means, let's say if I want to arrange, let's say we have n particles. Now I want to arrange them into ns, small ns, let's say ns, okay. So there is a particle with energy E0, there is a state with energy E0, okay, state with energy E1, E0, E1, E2, and so on. How many particles can be there in a given state? In a given state, okay, in a given state, okay, nr can be 0 or 1. That's all. Only two possibilities. Where n is stands for s. Okay, means here there may be 0, here may be 1, here there may be 0, and so on. But there is other possibility also. What is the other probability? Here there may be 1, here there may be 0, here there may be, and so on. How many such combinations are there? Many such combinations are possible. Let's now write down what is the photon mean number. Okay, photon mean number would be, let's say now, for particle mean number. So there is 0 particles, there is 0 particles, n0 is equal to 0. For which situation? Okay, for the situation where the E0 state is exploited, it is removed out, all the n particles are arranged in anything other than E0 state. Okay, right? So excluding a state with the Z energy, excluding the state with the energy E0 or epsilon 0, all the particles are arranged in n minus 1 remaining, all the particles are arranged in remaining states. Let me write down arranged in remaining states. Okay, what are those possible remaining states? There may be a state with n1, n2, and so on, ns1, ns plus 1, and so on, where the ns stands for E0 state. Okay, and what is the corresponding partition function of this arrangement? Is a ZS here. Okay, so let me write down overall mean photon number would be 0 multiplied by ZSN plus, now you see, one particle is arranged in E1 state. Okay, one particle is arranged in E1 state. Okay, so one particle is exhausted out of N. So remaining N1 particles are arranged in, okay, remaining N1 particles are arranged in, okay, in the other than E0 state. Okay, so these are the only possibilities. There is no other possibilities. So now mean photon number is the numerator divided by the total possibilities ZS n minus 1. You see the difference now between Bose-Einstein and Fermi-Dirac. Okay, so in a Fermi-Dirac, I have a possibilities of each state taking any number, but in the case of, sorry, in the Bose-Einstein, I have each state taking any number, but in the Fermi-Dirac, I have only possibilities 0 and 1. So both the possibilities I have considered in the numerator. The denominator, all the possible combinations were chosen. Okay, remember, I also should not forget exponential minus beta ES. Exponential minus beta ES. Okay, right? So exponential minus beta is also there in the first case, but it is multiplied by 0. So it is going to be, if you want, I can put exponential minus beta ES into 0, exponential minus beta ES into 0. Okay, so exponential beta ES into 1, exponential beta ES into 1. So what is the term I'll get? ZS, first term is gone, n minus 1 exponential minus beta ES divided by ZS n plus ZS n minus 1 exponential minus beta ES. Okay, now if you notice in the denominator and the numerator, one common factor is ZS n minus 1. What I'll do, I divide the entire equation in the numerator and denominator by this, the entire term. So when I divide, what do I get? Okay, what do I get? The first term numerator becomes 1, denominator ZS divided by ZS n minus 1 exponential minus beta es plus 1. Okay, right? So this can go to numerator 1 divided by ZS n minus 1 exponential beta es plus 1. Okay. Now, earlier we defined ZS by ZS. Okay. N minus 1. What we did define? Exponential. Okay. Wait a minute. Where is that? Yeah. ZS of n divided by ZS n minus 1 was exponential minus alpha s. Now we are doing opposite. So this is alpha s. Okay. Right? So if I do this, what do I get? Ns average number is equal to 1 by exponential minus beta es into exponential alpha s plus 1. In short, this is equal to exponential beta es plus alpha s plus 1. Okay, right? So the average photon number for Fermi-Dirac statistics, okay, this comes out to be with a plus sign. You see the plus sign here, but for the Bose-Einstein it is a minus sign. That is the only difference. So you can straight away say Bose-Einstein statistics average photon number is 1 by exponential minus beta es plus alpha s minus 1. For Fermi-Dirac statistics, Ns is average photon number exponential beta es plus alpha s minus 1. Very, very easy to remember. Okay. For Fermi-Dirac it's a negative. Sorry, for Fermi-Dirac it is a positive. For Bose-Einstein it's a negative. Okay. Now, what happens when? Okay. What happens when the classical limit is imposed? What happens when quantum limit is imposed? Okay. So when quantum limit is imposed, I should get some impact or some implication. For example, okay, for any value of alpha s, what is alpha s? Alpha s is a ratio, right? Alpha s is Zn by Zs plus 1, Zs n minus 1. Okay. So where alpha is just some factor. So for any value of this factor, 1 by exponential beta es plus alpha s, this quantity is going to be always less than 1 or be equal to 1 at the most. Okay, plus 1. Because for any value of alpha s, okay, this the entire factor is going to be more than 1 and it is dividing 1. So the overall quantity is less than 1. So which means, therefore, the Ns is average number going to lie between 0 and 1. Okay. Right? Okay. So this is actually Pauli's exclusion principle. Pauli's exclusion principle. Okay. This is straight away implication of no two particles can occupy a single state. Okay. Now, you keep all these things in mind. What we do, we will try to reach to a classical limit. Classical limit in the sense, we need to go for max Boltzmann statistics from the Fermi-Dirac or Bose-Einstein statistics. Okay, right? So quickly let me do that. Now, the classical limit of quantum statistics. Okay, there are two quantum statistics for us: Bose-Einstein, BS, and FDS. Okay, now as per both of them, the average photon number is okay, is equal to 1 by, okay, 1 minute. Let me shut down. Yeah. So as per this, the average for particle number beta ES plus alpha S plus or minus 1. Okay, fine. Where sometimes people write alpha, sometimes they don't write alpha. Okay, so you know that it's a alpha S is the ratio of partition function with n particles, partition function with n minus 1 particle arranged in some states running from n1 to n2, ns minus 1, ns plus 1, and except that ns state, how it is arranged. That is the alpha. Okay. I sorry, it's exponential alpha s, not just alpha, exponential alpha s. Okay. Now I want to know the classical limit, right? So classical limit. Now I will study this entire expression and see what happens. Now, as we just saw, the summation of all the particles is going to be fixed. Let's say all the particles are fixed. So, ns, average ns is fixed. Let's say there are so many ways I can arrange, all of them is fixed. Okay. So, if this is fixed means this term has to be a fixed, must be a small quantity because all such things are adding up to give a some n. So ns must be a small quantity. Okay. So when ns is a small quantity means what? Ns must be much less than 1. Okay. Like earlier we saw between 0 and 1. So let's say it's less than 1. Or you can say exponential beta es plus alpha s must be much larger than 1. Then only we'll have ns is less than 1. Okay. So when is this possible, by the way? When is this possible? Yes, just take the beta quantity, which is 1 by Boltzmann constant into temperature. Okay, Boltzmann constant. Now beta also should be a small quantity when t is large. When t is large, beta is small. Okay, large temperature I'm talking about. Okay, and also I will take a very low concentrated gas. Okay, for small n. Okay, a dilute gas. Right? In that case, n is small. Overall, average numbers summed together in various arrangements, they're also small. So the temperature is very large. So beta is a small quantity. Okay. So I will even say beta tends to 0. Right? When beta tends to 0, so the entire exponential beta es quantity also going to be 0. So what I will do, okay, what I will do, I will assume that some energy would be there, some ES would be contributing in this case. Means some energies are there associated with some particular arrangements. Okay. So in that case, exponential plus beta, okay, beta ES plus alpha S. Okay. So this quantity is larger than 1 or ns average is less than 1 implies, okay, right, implies a classical limit. Okay, so what is the implication of a classical limit on the Bose-Einstein Fermi-Dirac statistics is if you see, okay, if you just see NR, sorry, NS is simply going to be minus alpha s plus beta s in the classical limit, as this is much larger than 1. So exponential beta es plus alpha s plus 1 is equal to beta es plus alpha s. I don't bother adding 1. So, right, this also implies 1 by exponential beta es plus alpha s is equivalent, not equivalent, it's right away equal. It is equal to exponential minus alpha s beta es. So that is the quantity which we got here. So in the classical limit, we actually go to a max voltage 6. What is that? I'll just show you now. Now explicitly write down exponential minus alpha s into beta es. This is the quantity we have. Okay. By the way, what is this quantity? Exponential minus alpha s is, okay, minus alpha s is a ratio. Now let's forget that. Okay, let me use one more thing. A relation of summation over s ns is equal to n. We know this, which is equal to summation over alpha s summation over minus beta es, okay, implies various ns, na? Implies exponential minus beta es summation is equal to n multiplied by exponential alpha s. Okay, right? I can just send a rearrangement. Exponential minus alpha s is n by summation over ns exponential minus beta s. Okay, from the summation to like all the average numbers should sum to n, I got what is exponential of minus alpha s. Therefore, now average number would be, okay, n divided by summation ns exponential minus beta es into summation over, okay, exponential minus beta es. Okay, right? Yeah, there is no summation here in the numerator. So this is what we are left with. If you carefully see this, this is the quantity we got it for Max Boltzmann statistics. If you want, I can just derive or show you where did we have for a Max Boltzmann statistics. Max, yeah, you see. So this is a statistics. So the conclusion is, okay, therefore, as we go to classical limit, okay, Fermi-Dirac statistics and Bose-Einstein statistics, okay, reduces to Max Boltzmann statistics. That is a conclusion. Okay, right? Now we'll just give a 5 minutes break. After this, we'll just apply this whatever we discussed for one particle system or a two particle system, and so on. How this Fermi-Dirac statistics or Bose-Einstein statistics or Max Boltzmann statistics are going to help me to understand how the particles interact, right? How qubits are going to interact. That is the main strategy. We'll do it after 5 minutes. Okay. So don't worry, there is a notes is there for you people. So you can just go through the notes and understand. Okay, let me project the last part. the classical limit part. Okay. We are having a break, everyone, so we'll be back after a couple of minutes. Yeah, welcome back, everyone. So, right. So, what we'll do now, we just saw classical limit of the systems. Okay. Now, this is another way of saying, okay, so I'm not going to that. Okay. Now let's think about, okay, let's say a system of particles are there. It's consisting of single type of particles, say, let's say hydrogen gas or helium gas. There, all the particles are alike. Okay. So in that case, how should I treat those things? Okay. Right. So first I am going to say, right, let me use presentation writing here. Okay. First I'll think about, I have a state S. Okay. And the corresponding energy of that state is Es. Right. And the system is not interacting with any environment, not interacting with the environment. In that case, the energy of that state remains steady. Okay. In that, okay, fine. Now, the particle in that particular energy state is, as usual, specified by a position vector and momentum, and particle may be having mass m, and it is maybe confined in a volume v. Okay, let's say kind of a particle in a three-dimensional box, a 3D box, right? Now, as we know, a particle is specific, like put in a box. It is going to show, because of its quantum nature, I'm talking about in terms of quantum, it's going to be a wave kind of a behavior it is going to show. So the corresponding wave function, okay, the corresponding wave function is just like some wave amplitude will be there, exponential I into k r k dot r minus omega t. This is a wave function associated with the particle. Okay, what I mean is, I have written a amplitude here, which is the value is 1, for example, in our case, because we are treating with the quantum systems. So quantum state is amplitude 1. So the corresponding wave function is expressed in terms of radial part and the phase part. So this is a radial, this is a phase. Okay. Now in the phase part, what you see is the angular frequency omega is there. So I can write down the energy of that state as Planck's constant multiplied by angular frequency. Okay. Now de Broglie also says that de Broglie wavelength lambda d is equal to h by mv. Okay. And you just rearrange, mv is e is a momentum, linear momentum, p is equal to h by lambda. To multiply and divide by 2 pi, h divided by 2 pi is h hat, 2 pi by lambda is k, propagation vector. So linear momentum is equal to, and if I write down linear momentum in the magnitude, propagation vector in the magnitude, so relation between linear momentum to the propagation vector is, okay, simply linear momentum is equal to Planck's constant multiplied by kr. So that is what I have here. Now, what is the kinetic energy of the system? Let's say system is moving, kinetic energy. Okay, let me write down explicitly. Kinetic energy, which is half mv square. I can write that into potential linear momentum. So, magnitude linear momentum square by 2m is a kinetic energy. But I know propagation constant. Let me put in terms of propagation constant. In terms of propagation constant k, constant or a propagation vector. Okay, not the constant, let's say vector, propagation vector k. Okay, right? So Very good. Now, as you know, the propagation vector which connects to the energy. So I am just calling that energy of that state as ER, and where the wave function is having, or wave vector is having, propagation vector KR. Okay. Now, there is a scenario here. What is the scenario is, let's say I have waves going. If there is a reflection, the waves would reflect. Okay. And if they are perfectly reflect, what I'll have a standing wave pattern. Standing wave pattern. Okay. Let's say there is no reflection, or there is no reflection. In that case, what will have? Waves would be continuously propagated. At any point, if you just take the whatever wave was there here, okay, that let's say length L, the wave would have, okay, L plus X. The same behavior even after traveling length L. Okay, right? So, if waves are continuously propagating without being reflected, when it will happen? I'll take a very small particle in a very, very large box. Very large box. Compared to the size of the particle, okay, the box size is so big. So in that scenario, what happens is, we can show that the wave function, one minute, the wave function is simply going to remain the same at some point x comma y comma z, and later at a distance Lx. So that is what I wrote. Okay, so in case of three-dimensional box, I'll have x plus Lx, same value as the old value. Y plus Ly, the wave function remains to be same as the old value. Z plus Lz, the wave function remains to be same. So the length of the three-dimensional box I have taken is having dimensions of Lx, Ly, and Lz. Okay, so those are the dimensions I have. What it means? The wave function at some point x comma y comma z, same as wave function even after traveling a distance of L vector. What is the L vector? Lxi, Lyj, Lzk. Okay, right? This is associated with the wave function of the particle. Now, when is this possible? When is this about three equations are going to be possible is, okay, since I am talking in terms of exponential functions are sinusoidal cosine functions. Cosine functions. Okay. Exponential functions involves cosine functions. Right? So cosine functions means when such an equality holds good, only when kx into x plus lx is equal to some kx plus 2n pi, okay, where n is some integral or integer, okay, which means, okay, the wave must be traveling, and after distance L also, the value at old value, x value, same as L plus x value. You see, then only I can do that. Fine. Now, according to that, I can just simply write down an equation, kx and kx into x gets cancels. Okay. And what is remaining? Kx into Lx is equal to 2 pi by 2 pi into nx. So Lx you send it to the right, from left to right, you will get in the denominator. Same story would apply for ky and kz. Okay, the moment you know kx, ky, and kz, you can write what is a propagation vector, which is, okay, which is, wait a minute, which is kx 1 minute. Yeah, which is kxi plus kyj plus kzk. Okay. Now, what is the energy, by the way? Energy is, okay, as per our earlier case, energy is, where was the energy? H square by absolute kr square means magnitude square of the propagation vector divided by 2m. Let me write. Okay. So, energy is, okay, energy is h square by k square divided by 2m. So if we substitute what is explicit form of k inside, you will get nx square by lx square into 2 pi square, 2 pi square. Okay, yeah, and 2 pi square I can take it out. Sorry, 4 pi square. So 1 2 and 1 2 cancel. So another 2 is remaining. Okay, so I'll be left with 2 pi square h square by m. Nx square, ny square, nz square comes inside the energy. So this is a energy value of a particle confined in a given box, a large box, where particle would exhibit a wave nature. Okay. Now, right, so I can also talk in terms of density of states. What I mean is, particle can have a wave nature, something like this. Okay, wait a minute. Particle can have a wave nature traveling like this, traveling like this, traveling like this. Okay, no standing wave pattern, by the way. So the wavelength can be varied. So I want to know what are the various possible density of modes. The density of modes, if I want to know down, find out. You can also find out from the, okay, from how the change in k would induce the propagation, would induce, see, the propagation is changing here in all the 3 4 4 5 cases. So how is that change would induce the change in the number of particles falling into such kind of a wave nature? Okay, so already we got, okay, already we got energy expressed in terms of n is going to depend on k. So how is k is going to change the number of particles falling into particular energy level or energy state? That I want to find. What do I do first is, as I know, kx is equal to 2 pi by lx into nx. Now what I do, I'll just take a small change in dk due to small change in nx. Okay, so that is what I did. Now you just to do the rearrangement, delta nx is lx by 2 pi into dkx. Okay, now such a small change not only happens in x direction, also can happen in y direction and z direction, right, in all the 3 directions. So k, let's say k is varied from kr to kr plus some dkr. Okay, right? So within this range of propagation variation vector, how many number of modes can exist, wave modes can exist? That is a question. Let's say there are a dense of rho of k. Okay, right? The density of modes is rho. How many will fall in a small range of volume? We simply multiplied by density into the volume d cube k, and that is going to be equal to the rate with which small number of particles are changing in that particular zone. Okay, so then there is a delta x, delta nx, there is a delta ny, there is a delta nz. Okay, so explicitly I got for the delta x, delta mx, what is the expression would look like? You can just write down for delta ny. and delta nz. Okay, and if you carefully look at this, so the deviations with the kx and ky and kz is actually a small volume dv, okay, which is dqk. So this and this cancels. Okay, lx, ly and lz is a volume v. So v is lx, ly, lz. So there is a volume v. So that I will send it to the left. I'll get the density by volume is equal to, okay, 1 divided by 2 pi cube. So what do I get? It's just a constant. 1 divided by 2 pi cube is a constant. So the conclusion here is the right the number of states per volume is going to be very, very constant if I just take a dilute gas with a very single particle. Okay, right? Now, what would be the partition function? Those kind of a situation, you can get this using, see, energy I just got earlier. Use that energy. So as we know, the partition function is exponential minus beta es. Okay, so es we got. Okay, how many such es combinations are possible? Depending on the propagation vectors along the x, y and z. So I'll have different combinations. Okay, so you can separate into x and y and z, the partition functions. So basically the partition function is coming from x direction contribution, y direction contribution, and z direction contribution. Okay, so not going to the details, I can straight away show you what is the partition function would look like. It will have the length of the dimension of the system in the picture. It is also going to have the mass of the particle in the picture. So other than that, everything else is constant. Okay, right? So you can just skip this for time being. Right now, I can also find the energy, sorry, entropy and those things. So entropy from the partition function. We'll skip it for now. It's a little bit now too much. Okay, next thing is polyatomic molecules. Let's say there is a gas ideal gas consisting of n polyatomic molecules. Means there is a molecule with two types of atoms inside. Okay, it's not one single type in the gas, so two types. So let's say earlier I took single hydrogen atoms in a gas. Now let's say hydrogen H2 is there, not H2, maybe H2O, with hydrogen and oxygen is there. So such kind of where two different kinds of systems are there. Okay, or at least two atoms are there or more in that particular gas. In that case, what would be the partition function? Okay, right? So there will be partition function for single particle and two particles together, and there is something like grand canonical partition function you would have to write. So you keep that aside. Let's understand from the perspective of Hamiltonian, right? So now the two particles are there. Let's say one particle moves around the other. Okay, so there is a translation motion. Okay, for example, nucleus and electron kind of a thing we are talking. So translation motion is there. There is a motion of the electron about the nucleus, and the entire setup is translating. Okay, rotation of the molecule about some center of mass, that is also there, and there may be a vibrational motion of between the molecules. So there are various possible motions and their corresponding energies may come into the picture. So you have to write the Hamiltonian accordingly. Okay, right? The moment you write the energy of the system, it's a partition function writing becomes very easy. So it's simply exponential minus beta into the energy of particular arrangement. How many such arrangements are there? There may be a translational motion, there may be electron motion, there may be rotational motion, There may be electron motion in the sense electron can spin on itself. That is what I'm talking about. There is a vibrational motion. Each motions can be in multiple ways. For example, electron spin, if you take, it can be upspin or a downspin. So there are two combinations. So that has to be their energies are different. Upspin, there is energy value is different. Downspin energy value is different. So there is a vibrational values. There will be vibration is happening in a particular fashion. Horizontal vibration, vertical vibration. Okay, so all those vibrations can come in and contribute differently. So according to that, I have to write the Hamiltonian and the energies. From there, the total partition function would be a various arrangements of partition function together, just some like a product. Okay, for example, diatomic molecule partition function. So now diatomic means two different. One is M1, another one is M2. And what is the overall mass? M plus M1 plus M. In that case, what is the total energy of the system? Means Hamiltonian is translational Hamiltonian means the entire center of mass is moving like a single particle. So which is just a linear momentum of the single particle divided by 2 into the total momentum of the particle, the two particles, total mass of the two particles. So total energy also you know. The moment you know the energy, okay, you can find the partition function. Now I don't see a, okay, in terms of exponential minus beta energy, right, of the system. Why I don't see is I straight away used the single atomic case. What was the expression? What was the expression? This expression I'm using straight away. Okay, in the diatomic case. You see? Now, okay, let's apply this for the case of electron motion inside a molecule, as inside an atom. Okay, so usually if you plot energy of the particle or an electron with respect to distance away from the nucleus. Okay, so initially the energy is very, very large. It comes down to very, very low value at some point, ultimate steady state point, and then it starts picking up as some external energy is supplied. Okay, right? So in this case, if I want to write down partition function, okay, who is supplying energy? There may be external temperature may be coming in. They may be supplying energy. In that case, the particle is actually a jump from one orbit to other orbit. That is what we see. So nucleus is there. There is a ground state. There is a excited state. Okay. I was referring earlier. So between 0 to 1, the particle has to climb kind of a hill and then go to the other side. Okay, so that is what shown here. Particle is having very low energy. To acquire higher energy, it has to jump the hill and go to the other side. So in this particular case, what is a partition function? Arrangement of electron in various states is represented by some partition function where, okay, omega naught, this is called capital omega. Capital omega naught stands for degeneracy. Degeneracy in the sense, in a given state, two particles can be put if they are provided with the opposite spin. Okay, so that is what captured here. Now, rotational motion contribution to the partition function. How should we do? So first of all, if two particles are there, M1 and M1, okay, they are together like a molecule, right? So if they are rotating about something, so they are going to have some kind of a what is called a rotational angular momentum. See, angular momentum, which is represented by J, angular momentum number. J is quantum number, so which can take values 0, 1, 2, 3, and so on. And the angular momentum value is h into j. That is just like a spin. The spin angular momentum, rotational angular momentum is represented by j quantum number, and its energy value, sorry, angular momentum value is just h into j in the units of h. Okay. Now, what is the energy of such motion? Okay, energy of such motion is h into j square divided by 2 into I. If you recollect back, what is the energy in terms of kinetic energy, which is p square linear momentum square by 2m. You can just see in place of linear momentum, I have angular momentum, rotational angular momentum square divided by 2 into, in place of mass, I have moment of inertia. Moment of inertia. Okay, right? For diatomic molecules which are contributing for energy, they will come inside the partition function. Right now, j square, I'll just write it as a j and j plus 1. Since I can't have various possibilities with just a j square, so various possibilities can be captured by converting j to j into j plus 1. Okay, just a similarity symbol will write. Now, what are the possible ways this the spin quantum number, angular spin quantum number mj will take? Okay, j is an integer, and what is a angular momentum spin quantum number would take? It starts from minus j to plus j, okay, and goes up to 0 value. Okay, right? So this is a specific energy. And now using the specific energy for various possible arrangements of rotational angular momentum, you would just sum various combinations, you would have a partition function taking all how many possible scenarios? 2j plus 1 scenarios. Okay, right? And also you can get rotational energy divided by thermal energy ratio if you just see it, okay, which comes out to be much larger than 1. Okay, right? When t is large, it comes out to be a very small. When I is not too small, okay, so that is a case situation I considered. So I think the limits may not matters much. Only what matters is temperature. Okay, right? Okay, so what else I have? Okay, I quickly show you vibrational dynamics contribution to the partition function. So I have discussed that vibrational contribution, how it needs to be incorporated. You can check that. Collection of photons inside a container. In that case, what is the wave equation? We have seen that earlier, I think. But if you want, you can, from the Maxwell's equation, you can derive wave equation. Okay, wave equation solution is just a sinusoidal solution. The moment you know sinusoidal solution, you can apply whatever we did earlier. You can find number of modes, density of modes inside. Now you can apply the Bose-Einstein statistics for this case and get, okay, and understand how, okay, how electromagnetic waves are quantized as per Bose-Einstein statistics. As per, okay, as per Bose-Einstein statistics. Okay, so now let's summarize what we have done so far. Okay, now so far from the past 3 to 4 days, I'll just summarize. So we addressed how quantum particles are reacting together. Okay, how we did this? We used a probability distribution. Okay, distribution of their existence together, which is done through Gibbs principle. Okay, and next, particles treated as classical and also quantum. Inside a quantum, Bose-Einstein and Fermi-Dirac. classical case Max-Boltzmann statistics. Okay, right? So there may be flipping or transfer between this quantum to classical when I implement some conditions. Those things we discussed. So overall, we have explored dealing with the identical particles. Even though they are identical, when it comes to max real world scenario, we can identify them, where their location and how they're placed. Okay, when it comes to quantum, they're indistinguishable. Okay, and in that case, either they can be arranged in same location, many particles, that will be Bose-Einstein, like a photons. They cannot be arranged in same location, like an electron inside an orbit. So that is actually the implications comes from the statistical physics, and Pauli exclusion principle was also derived from the statistical physics. Okay, so I'll stop at this point. If there is any questions, I will take the questions. Arka sir, I don't know whether the voice is breaking from your end for me or for other participants also. Can you please check? Your voice is slightly breaking.
Maybe, sir. Is my voice clear, sir? Voice is breaking.
For all, sir. Yeah. The participants are saying, yeah, voice is breaking.
Device में दिखा था. Is out. Calendar. Anil sir, chairman sir will also join.
Yes, sir. Yeah, actually, I'm out of station.
I think it's
I requested, I sent a message, but he is in another meeting, may not likely to join, sir.
Right. We sent this thing actually invite already. Panel. Right. Take care, sir. Okay, sir. Ashwath sir, you are saying something?
Yeah, it's improving. The voice is improving. Not an issue.
Yeah, anyway, we'll connect from another device.